Mastering Lambdas. In this section, we're going to take a look at Lambdas in the standard library and the way they interact, Lambdas as local functions, including the IIFE idiom, and finally, how to use higher order functions to build safer interfaces. Let's begin with the first video, Lambdas and the standard library. In this video, we're going to take a look at using Lambdas with algorithm, thread and future, and tuple. Lambdas and algorithms interact well together. The standard library provides dozens of algorithms that accept one or more function object parameters. Most of them reside in the algorithm header, while others, like SED accumulate, reside in the numeric header. The standard library provides dozens of algorithms that accept one or more function object parameters. Most of them reside in the algorithm header. Others, like SED accumulate, reside in the numeric header. Here's a very simple algorithm, SED for each. I've taken a screenshot from a CPP reference that shows the various signatures available to the user. As you can see, for each takes an input iterator as the first, an input iterator as the last, and then a unary function f that will be invoked on each element of the range determined by the two iterators. Since C++17, there's a new overload that accepts an execution policy, which allows you to automatically parallelize your algorithm. Here's a simple example. I created a vector of integers with 0, 1, 2, and 3, and then I pass begin of v and end to v, and a lambda to SED for each. This will invoke this closure over here on each element inside this range. Since C++17, as I said in the previous slide, you will be able to specify an execution policy. You have a sec execution policies, a par execution policy, and a par unsec execution policy. The first one tells the algorithm to be run sequentially. This means that it will not make use of any parallelism. The second one means parallel, and it will allow the algorithm to be run with multiple threads. The third one will not only allow the algorithm to run in parallel, but will also allow the algorithm to be vectorized. All of these have different guarantees and rules that you should check out before using an execution policy for your algorithms. Assuming that in this example here something is a function that can be called safely by multiple threads at the same time, then I can simply add execution par as the first argument of for each, and this will be parallelized for me automatically. I really like this family of three algorithms, all of, any of, and none of. What they do is really self-explanatory. Given a range and a predicate, they will return whether or not that predicate satisfies all of the elements in the range. These algorithms can substitute very unintuitive loops written to express the idea of all, any, or none. Let's take a look at some examples. Imagine that we have a struct called person that contains a name and an age, and a vector of person called ps. If we want to know whether or not all the people inside the vector have reached the legal age to drink, we can say something like const bool can drink equals SED all of the range of ps and this lambda here that will return whether or not the age of some person is greater or equal to 21. This is a very intuitive and terse way of checking whether a predicate is applicable for every element inside the container. Now imagine that we get in the data for the people from some service, and we might have some missing data for the names. If we want to check whether or not all the people in the vector have names, we might say something along the lines of SED none of, using a parallel and unsequenced execution policy, the range of the vector, and this predicate over here, which returns whether or not the name of P is empty. And we can read this as all the people have names if none of the people inside the vector have an empty name, which is really intuitive and powerful. Other two very useful algorithms are SED count and SED countif. Count in this case simply takes a value to compare to and will return the amount of occurrences that that value appears inside a range. Countif, on the other hand, takes a predicate and it will return the amount of occurrences an element inside a range satisfy the predicate. This is a great opportunity to use a lambda. Imagine you're writing some sort of game where players have a level, and you want to run some statistics and see how many of your players have reached the high level of 70. You can simply say something like SED countif begin of players, end of players, and then a predicate that will return whether or not P has reached level 70. This kind of terse and intuitive code is made possible thanks to lambda expressions. Another nice algorithm that should be, in my opinion, used more often is STD partition. Given a range and a predicate, it will shift around elements inside the range to bring all those elements satisfying the predicate on one side and all the elements not satisfying the predicate on the other side. Here's an example. Imagine that we have a system where we have string IDs, and IDs referring to users begin with a U dot notation, and IDs referring to groups begin with a G dot notation. And let's say that we have an heterogeneous set of IDs, and we want to partition it so that all the users are on the left side and all the groups are on the right side. We might invoke STD partition as follows. First, we pass the begin and the end of a range, and then we provide a predicate that checks that the first two characters of the string are U and dot. What we get back is an iterator IT, which represents the splitting point. If we use STD for each from the beginning of the IDs to the IT, we can print out all the user IDs. And if we use it again from IT to the end of IDS, we can print out all the group IDs. Another very powerful algorithm is STD max element. Given a range and a predicate, given a range and a comparison function, it will find the maximum element with respect to the comparison function inside the range and return an iterator to it. Here's an example. Imagine that we have a vector of music tracks and we want to find the longest song. What we can do is STD max element with the begin of songs, end of songs, and then provide a comparison lambda that gets song A and song B and simply returns the comparisons of their duration. This will return an iterator pointing to the longest song in the vector. The takeaway here is that any algorithm that takes a function object or a callable as a parameter can benefit from lambda expressions. Your code can become more expressive and shorter. Since C++ is 17, you also have more reasons to use algorithms, as they can be automatically parallelized thanks to execution policies. If you want to see a very nice reference for the algorithm header and the numeric header, as always, I recommend the CPP reference pages, which are very thorough and very informative. Let's now take a look at how lambdas can help with multithreading. Since C++ 11, the standard library provides a lot of useful multithreading facilities. STD thread is the basic facility that represents a thread of execution, and it allows the creation of a thread that executes a given callable object. In this case, I'm creating a new thread T, passing a lambda as its argument, which will sleep for 100 milliseconds and then print out world. After creating the thread, I immediately print out hello and then join to wait for the thread to finish. This will print out hello world, as the thread will sleep and will leave the first stdcout call a chance to be executed. Lambdas make it easy to invoke member functions asynchronously as well. Imagine that we have a myFoo object of type foo, which provides the f0 and f1 member functions, and we want to run both of them at the same time asynchronously in separate threads. What we can do is use a lambda to capture the instance of foo, pass it to a thread invoking myfoo.f0 or f1, and then do something while this is running in the background, and finally join the threads to wait for them to finish. Another really useful utility introduced in C++ 11 with regards to multithreading is STD future. It takes a template parameter t and allows us to asynchronously compute an instance of t and get it later in the future. You can think of it as a promise that will give you an instance of t later in the execution of the program. If you have some sort of long-running computation, you can simply invoke a function that returns a future to it, and while it's running in the background on some other thread, you can do other things, and then you will be able to get the result later in your code. Instances of STD future that run in separate threads can be spawned by using STD async, which is another standard library facility. In this case, in order to guarantee that a separate thread will be used, you need to use the STD launch async policy. Let's take a look at some examples. A basic way of creating a future through STD async is simply creating a variable and initializing it with the return value of the STD async call. In this case, I'm using the async policy to make sure it will start another thread, and in the body, I'm sleeping for 1 second and then returning a value. While this is running in the background, I can do something else, and then finally, I can assert that f.get is 42. In this case, f.get will immediately return if the computation was completed by the time I ended up here. Otherwise, it will block and wait until the computation is completed. Boost future, and soon SED future as well, will allow asynchronous computation to be chained by using .then when all or when any. This allows you to define graphs of asynchronous computations that might depend on each other, which will execute in parallel when possible. In this case, I'm using boost async to launch some HTML GET request of some URL, and then using the .then member function, I'm chaining another operation by using a lambda that takes the previous future as an argument and provides a subsequent computation to execute. There is another utility called boost when all that, given any amount of futures, in this case spawned with async, it will execute them in parallel, and only when all of them are finished, it will then continue on to the then continuation. So as you can see, you can create some sort of really complicated pipeline where you have multiple things depending on each other, but it will always try to execute as many things in parallel as possible, respecting dependencies. In this case, I'm simulating to get requests in parallel to different URLs, and then when both of them are done, I will get back a future representing the finished computation of both of them. And then I can use it to continue my computation later on in the program. Let's now look at how lambdas interact with tuples. SED tuple of TS is a fixed size collection of heterogeneous values. As an example, you can say SED tuple of int, float, and char, t, and initialize it with an int, a float, and a char. And this will basically store them as if they were in a struct. Lambdas can help us here invoke an existing function objects with the elements of the tuple or iterate over a tuple's elements. In order to do this, we need this new great utility introduced in C++17 called SED_apply. SED_apply takes a function and a tuple, and it will invoke the function by unpacking the elements inside the tuple. Here's a very simple example. If we have a tuple containing two ints, t0, that contains 1 and 3, then we can use SED_apply to invoke a lambda taking two ints by passing the tuple as a second argument. Apply will unpack the 1 and 3 for us and pass them as the argument of the provided lambda, which in this case will simply return the sum of their arguments. If we use SED_apply on t0 and this lambda, we will get back 4, which is the sum of 1 plus 3. Lambdas make it easy to extract the sum functionality and apply it to other tuples. What we can do is create this new sum lambda that takes a tuple and then returns SED_apply of the previous lambda and the t that we're taking as an argument. In this case, we don't have to bundle the logic that I want to execute in the same place as we have the tuple that we want to call the function with, but we can simply say sum with a tuple and get back the result we expect. In this case, the lambda is allowing us to bind this lambda here as the first argument of SED_apply and then generalize it over the tuple parameter. By combining lambdas and C++17 fold expressions, we can easily iterate over tuples elements. And by iterate, I mean generate code that will be executed for each element of the tuple, as a tuple is an heterogeneous compile time construct which cannot be iterated upon at runtime. In this case, I have a tuple of int and char, where my int is 42 and my char is a uppercase x, and I invoke SED_apply by passing a lambda that takes a variety amount of arguments and the tuple. What will happen is that this lambda will be invoked with 42 and x. And now I'm using a C++17 fold expression that will stream all the elements inside the XS parameter pack to SED_cout. If you're not familiar with this syntax, this basically means to expand every element contained inside this pack as part of this streaming operation. The final result is 42x. If you think about it, this is a way we can model iteration over the elements of a tuple as we are executing a particular operation on every single element contained inside it. We can generalize this again by using lambdas. We can create this construct called forTuple that takes a function and a tuple and calls SED_apply for us by providing a variadic lambda which takes all the elements inside the tuple, forwarded here to SED_apply, and then again uses another C++17 fold expression to invoke f on every single element of the tuple perfectly forwarded. In this case, we can say something like a cd tuple of int and char with the previous values, and instead of explicitly using a fold expression inside apply, we can use for tuple with a lambda that takes an element of the tuple and simply prints it out to the cdc out. Using this order construct allows us to, for example, provide a separator between the elements of the tuple. Note how for tuple is basically std for each, but for tuple elements. And also note how we're using auto in this example because we need to make sure we can handle all the different types contained inside a tuple. Here's a quick recap for this video. Most algorithms in the standard library greatly benefit from lambda expressions. This allows you to make your code more expressive, shorter, and way more intuitive. Spawning threads and futures with lambdas is also an intuitive way of creating asynchronous computations. Combining lambdas and std apply allows us to easily manipulate std's tuple elements and create some very useful utilities and abstractions that allow us to either call a function with the tuple elements or iterate over them by generating code for each element. Here's my guidelines. Unless you have a very commonly used or long predicate, always prefer lambdas instead of structs or non-member functions for algorithms. For simple asynchronous computations, prefer in-place lambdas. More complicated pipelines will benefit from having named function objects. These could be lambdas themselves, or structs, or non-member functions, but I strongly suggest you to bind them to some name, either with a variable or with normal function syntax, in order to make your asynchronous computation more composable and easier to understand. Also, here are some references about C++17 and the new feature in C++17, and this great book by Anthony Williams, C++ Concurrency in Action, which gives you a very, very thorough overview of the C++11 multithreading facilities and a lot of realistic use case examples.